speaking at Kakalaki-Con. In its previous history also. So, Deral, Heiland, Principal Security Researcher at Rapid7. There's no sense in wasting time on me. That's boring. So let's go ahead and move into the talk. So we're here to talk about IoT technology and cellular technology within IoT specifically. So this is a project that I started about a year or two ago. It was like, as we see this growth in cellular technology and IoT, either used in like home security systems for backhaul communications. We also see it in remote camera devices. The device I'm actually going to be using in demo today is a trail camera, battery operated trail camera as an example. And as I've started looking at these devices and trying to observe them, I'm going to try to share a lot of different topics in this area, and I think it's kind of fun and exciting, and hopefully you enjoy it too. If you have any questions, it isn't like we got such a large audience. Feel free to raise your hand if you have something to say or a question to ask about it. So first I want to start off with an intro to cellular technology. Not all cellular technology, but what we typically see utilized in IoT. It isn't like cell phones, cell modules, which way more bandwidth. You know, you're downloading your internet, you're taking pictures, there's just all kinds of crazy things going on. IoT-based technology usually is quite different when you talk to cellular. So the whole group is maintained by this group called 3GPP, I think tells what it is there. That group actually doesn't run the standards, but it runs all the organizations that run the standards. So they kind of oversee the whole picture. And what you think about in IoT-based cellular, three general areas. You're looking at things that are size, smaller, has to go into a smaller device in some cases. We're also looking at costs. Obviously, if it costs $200 for a cellular module in some cheap, crappy piece of IoT, it's never going to be there. So it has to be cheap. And then we get into power. Power consumption is always an issue because you're dealing with devices that may be battery operated. So if you want to do transmission of data, if you consume a lot of power, you're going to drain the batteries quickly. So these devices fall into those categories. Two general type of devices we call NB-IoT and LTE-M. There's a couple different versions, each one of those. Real quick on the NB-IoT, this kind of functions in several different modes. You have LTE in-band, which is communication goes in the actual LTE bands. You have guard band. So when you start looking at the channels or the bands in the LTE signal range, there's gaps between those. So a device can actually communicate out of those or in between those two bands. It's known as guard band area. And then you get standalone. Standalone, they actually utilize the earlier standards for the most part, and it's usually focused to specific functions and services. They often have two types of power controls in them, discontinued reception. Obviously, you don't want to consume power. So if you're not transmitting anything, you don't keep signaling. Reduce the power consumption. The other is power saving mode, and you'll actually see it happen on this device. This device will come up running, it'll do a bunch of transmissions, it'll turn around, and it'll power the module down. And you'll see that. And that's done to actually improve power consumption on these devices. So there's two main ones when you get into NB-IoT, NB-IoT 1 and 2, and you can see the download peak speeds, very low. We also notice they're half duplex. Again, these are just passing telemetry data, so you're not going to move voice or SMS messages or anything like that. It's pure telemetry data. It's a quick measurement. Hey, you know, this thing has this much pressure and off it goes, or it's going to be this little piece of data and off it goes. It's basically telemetry data moved on these. And then we get into LTE, M1, M2, or Cat1, M1, M2, ever how you want to call it. Different names are used. It's higher complexity, may more features, functions, capabilities. We also see lower latencies. Obviously, in this case, you're moving more data, so you don't want to, or more critical data in some cases there, so you don't want to have the excessive latency associated with it. It does only in-band LTE communications. It doesn't do the other two weird things. And then we get into power. You still have the same power consumption issues. Again, these devices that are on this device, I think is an M2 communication type device. So it actually does the same power things to keep a reduction, because this device that we're actually looking at, playing with, is battery operated. Obviously, I'm not running batteries on it because it'll take 12 volt input also. But if you want to put it in the field, it's going to be battery operated. Again, main two standards on those, and you see the different down peak rates and uplink rates. Much more data. You can actually make voice calls over these two devices. So I've actually taken, not this device, but I've taken other devices that are IoT devices that had one function, and actually have made voice calls with them by hooking into it and connecting up and actually making voice calls with IoT device to prove that it could be done. Haven't done that with this one, but we're going to do some other similar stuff so you can see how to control the device in an IoT device to get it to do other things you may want it to do. And again, you look down here, and as you can see, the speeds, full duplex. It could do half or full duplex. So you're signaling in both ways. Better performance for more bandwidth type data that you need to use. A camera, you're moving images, you're moving video, things like that. You have to be able to have that full duplex to be able to get commands into it, to send data up, all that type of stuff. Any questions? So now you know everything there is to know about IoT-based cellular tech. Also, there's some new release versions. So I spent some time looking at these going, is there anything really seriously impactful that we need to address today? Not really. So you get better efficiency in network operations. They've improved in that. Access control, small cell support. Basically, small cell is a micro environment for cellular where you have a higher density of devices and be able to support higher densities within those areas. Let's say you want to put in some kind of control systems within a large hotel where you actually have hundreds or several hundred devices. You may want to set up a small cell type environment to be able to handle that density and bandwidth associated with it. Again, he actually made more power improvements. I don't know what that means. I just know without reading a lot of the standards, and everyone knows reading standards is somewhat painful. And of course, 5G services and features were added into some of these releases, I think in the later releases. I think it came out in 15 or 16, and then obviously more improvements that we moved to release 17 of that. So now we've covered all that. So let's dig into the dirt now. So let's look under the hood. So when you start thinking about modules we've seen in devices, these are the typical manufacturers, Quintel, U-Block, Sierra, whatever. Telite and Centeron actually merged here last year. I like the Centeron devices, and I'll tell you why I like them. Often, if you want to get a development kit for one of these devices, for every one of their modules, you have to have a development kit. It gets kind of expensive. Centeron came out with one that had a socket. You could buy 2 sockets for one development board, cover every module produced. Big savings. It costs a little more than most of the devices, but again, I can test and interact with all of their devices using one $700 purchase versus a $300 to get through their whole series of devices. I was out at CES this year, and I ended up talking to Quintel and U-Blocks, and I actually spent most of the conversation scolding them on cheating me on development boards and why aren't they doing what Centeron's doing. And they admitted, man, what they're doing is really cool. We should do that. So hopefully they took that back and do something with it. If you look under the hood of these devices, every one of them have Qualcomm chipsets. That is the standard throughout. Is there any exceptions to that? I have not found it yet, but I have come across devices that had cellular capability that did not use modules. They cooked their own solution actually on the main control boards. In those cases, I saw Qualcomm's and some other devices also used within those environments. So let's go through a teardown. Often when I pick up a new module or a device that has a certain module, I want to dig in a little deeper, go a little further. How's this thing work? I've actually been paid to do this in the past by certain vendors. And what I do is we start taking it apart. So in this case, we've actually unpacked it, and these devices are packed in tights. So you're looking at a fairly small device, and you can see how small these devices are here, and you can see how packed the components are. So literally, I go out and buy the cellular modules. First thing I do is I throw it in an oven. I heat it up, and then I scrape all the components off of it. I want the circuit board. I want to know what's going on with that circuit board. So when you think about these devices, they're just another circuit board. And then those are attached to the board within the IoT technology. And the connections under the underside of it, instead of being like ball grid array, they're known as LGA, land grid arrays. They're larger square pads typically. So if a vendor, certain services or functions on this, if a vendor puts the device on their box, in their device, there's certain things I may want to look at, and they're not always easily accessible. So I always want to say, hey, can I attack these from the surface and dig into them? So that is like a land grid array for this, which I think it is the EG91. And we start looking at the layout up here after it was cleaned. That's where the flash memory sets, and that is a BGA multi-chip package, which we're going to get into a little deeper here. And the other part is the actual CPU. So I'm always curious, can I get JTAG on there? It's not always easily available on these devices. So what we do is take the chip apart. If I can get a data sheet, I try to identify all the JTAG connections, and then I trace it out on the circuit board. So the best way to do that is if there's no components on the circuit board. So that's why I strip it clean. And those are messy. If you went into my lab and you walked out and actually looked at the bottom of your feet, you'd probably find all kinds of micro resistors and components stuck to your feet. It's kind of insane. I always tell my wife, don't bring the dog in here because I don't want these components all over the house. So it can get really messy, but we can dig into it. So the next thing I want to look at is memory chip. We saw the memory chip was on there. These memory chips, even though the ball grid array structure on this, 162 balls, it's about 1/4 millimeter approximately each one of the pads. This is an MCP, which is very different than an eMCP. These are multi-chip package, meaning they contain flash memory, usually NAND flash memory, and RAM on the same chip body. So when I first saw one of these things and I didn't have a data sheet, my first thing is it's just an eMCP, which is an embedded controller. Those have an embedded controller on them. So if you find an eMCP, there's readers that you can buy for like $100. You just drop the chip in, plug it into your box to the USB. It'll mount up the entire file system for you automatically because it has a built-in controller. You're not lucky with that here. Also, if you want to take it any further, chip sockets for these are horribly expensive. When they first started using them on a larger scale a couple years ago, to buy a chip socket for a flash memory reader was upward over $2,000 for a socket. And that happened to be a socket based on the dimensional size of the chip. Not all chip dimensions are going to be the same. Some of them will be 11 by 10s. I've seen them 10 by 10. They'll be 9 by 11, all different measurements. Well, the sockets have come down now. They're only like $600 or $700. Unfortunately, most of the reasonably priced chip readers can't read these, okay? They don't have this particular devices in it. You can buy chip readers that do. You're paying into the thousands. 3, 4, 5, 6,000 for a high-end chip reader to be able to do that. And then you're dropping another $2,000 to $4,000 for sockets to be able to read these. Well, I'm cheap, but I'm not lazy. So what we do is we find out that the 162 ball grid array of these devices is identical. It doesn't matter who the manufacturer is. So if you can get a pinout design for any one of these, you can identify key components. So if you look up the top where the upper green or turquoise looking one are, that's the flash memory location. There's a paper that I put out, or actually a blog I put out, where I detail the process here of actually dead bugging these. So the way we dead bug these and make it easy, well, I think it's easy. I think everyone should think it's easy. So go look at my blog. So what we do is we identify these, map it out on the chip, and then I ball the dice. I actually add 0.25 millimeter balls or 0.3 millimeter balls based on the size of the pad, and I flow them onto there as a landing point. And then what we do is we hand wire them up. So if you looked at my badge soldering, you go, he's not capable of doing that. I do that under a microscope. When I was doing the badge in the other room, the lighting, these typical type of lighting, makes it nearly impossible to do good soldering. And then you take into the fact I'm an old man, it deteriorates quite rapidly. I still soldered it, and I looked at it real close, and it came out pretty good for somebody who couldn't see anything. I usually want to pass this around so you can get a closer look at it. I think it's here. So what we do with that then is I build basically a ZIF socket breakout board. And I use these for dead bugging. So I pass this around so you can see the chip and the wires. This was one off the EG91 I just wired up and read it and got all the flash memory off of it. I already got the flash memory off of it, so if it gets busted, don't worry about it. Okay, so like I said, we wire this thing up, we drop it into a reader, but I already told you none of the readers can actually read these things. Well, manufacturers of chips don't create new chip silicon for everything underneath the sun. What they do is they just put it in a different package. No different from this. So then you have to figure out what of all the chips that they produce is most likely to be what's underneath the hood of this one. And you do that with no data sheets, because most of these don't have data sheets. But it's fairly easy. You have cell slicks on these things that tell you things like, hey, it's 8-bit, so many bytes, it's a different structure size, and you get that information, and you just search through that manufacturer's list of chips. I typically like to look for ones that are TSOP 48 or 48-pin chips that would potentially have that same silicon underneath them. And then what I do is I wire this thing up like it's a TSOP 48. Plug it into my socket and pick one of their things. In this particular case, when you read this in a flash reader, two things will happen. Either it'll recognize the chip ID, because the first thing it does is it checks for the chip ID. If the chip ID matches, it'll read it out to you. Turned out this one actually matched the chip ID, so my first pick was right on the first time. And that's amazing considering these places produce hundreds of different types of flash memory chips. If it is wrong, and you know the data of this flash memory matches the data of what you're looking like, the voltage and all that type of stuff, just tell the chip reader to ignore the actual chip ID, and it'll still read all the data out of it clean. And I've done this with dozens of different chips many times. On these particular chips, I haven't run into this, but I've run into certain weird BGA chips where I was able to do this same attack on those. Recently, about a year ago, one of the guys on the team go, I got this chip, I don't have a socket for it, I don't know what it is. They just drop it in an envelope and ship it to me. I get the chip, I analyze it, I do this type of attack to it, and it turned out I did find a data sheet of the pinouts on the back side of it, enough for that information, and was able to match it up to a TSOP for the silicon. But one thing it kept throwing me, it wouldn't read. So I went back to, not the data sheet, but the pinout, the structure. It showed it, and it actually lists VCC1, VCC2, VDD1, VDD2. Turned out, even though the voltages in the ground were typically acceptable common, they were not common inside the chip body. So that's where those jumpers are on that particular one. So I just jumped it out on my chip reader to lie to it and added to two new wires for each side of that to make that happen. So interacting with hardware. Yes, sir?
Is that with the separate VCC power and ground, is that because it's a multi-chip package?
No. The one I seen it on wasn't multi-chip. It was purely a NAND flash. I just bring that up because it bit me in the ass on something else, and more likely if you're doing this type of stuff, you're going to come across that eventually. So it was different power, different ground. They were split on the chip. I don't know why. Absolutely know why. But it turned out as soon as I corrected that, the chip read instantly. In that case, I did not have a match for the TSOP style silicon. But I just told it just ignore that, and it dumped everything fine. And again, that blog I put out goes through the whole process. Yes?
Is this the firmware for the whole device or just the cellular modem itself?
Just the cellular modem. So today we're not actually going to look at anything on the device other than the cellular data and look at that. The actual get into the CPU and that flash memory, if you're doing an overall assessment of a device, you're going to pull that too and look at it. But in this case, I want to talk purely cellular. How does that impact these devices? What can you look at? How do you interact with it? So extracted firmware, interacting with hardware. We're going to dig into this a little bit. So this is not this particular device, but I wanted to share this. It's kind of approach. This approach will work on any kind of hardware you're messing with. And the way it works is, so we have this device. They're multi-layer boards, but we have at least two layers that have visible components on it. How do we figure out and track things down? So what we do is we transpose. So as you can see, we can transpose both sides on each other. And from there, we can identify relationships between one side of the board and the next side of the board to help us figure out where the possible communication lines are coming from the cellular module. And then we overlay a grid off the cellular module on top of that. Because often, not always, often if you're looking at something, you go, hey, here's UART, or hey, here's USB. Where do you think that could come to the surface? It's probably not going to do it on this side. It's not going to do it on that side. More than likely, it's going to do it on the side that data's at. One of the things you think about, I don't even know if I have a picture, when you're looking at these devices, is that every one of the cellular modules I've looked at, talking about IoT devices, the NB-IoT and the Cat M1, M2, most of the important stuff are always going to be along the outer edge of the chip. And I want to talk about something, but we'll get through this right now. So we knew where the communication lines were potentially at. And so you can see, so if we even go back further, and we see on this side, we see the wires I've attached to it. That's actually attached to the UART communication on this particular device. This device wasn't using USB for communication. It was doing it all with UART with this particular chip. But we wanted to map that out, so we get around to doing that. And we need to wire up to it. And if you saw my talk last year where we were talking about interchip analysis, interchip communication analysis on IoT devices, one of the things I like to do, especially when we're dealing with UART, can't do this with USB, but with UART, we can actually cut the runs. So what I do is I cut all the runs between the main processor and the other communication devices communicating with. And then, let's come back here. And then I bring it out to a breakout board. And then from the breakout board, it has an on and off switch. You'll see one later on in here from that device there. That gives me the ability. So if I want to inject data into the UART communication on a device, if it's fully in circuit, you're not going to be able to do that. It's just going to ignore that. The way to do it is break the connections. You let the device come up to full operation. You throw the switches. You have your devices hooked to it. Now I can inject data in and control components or send other communication to the device. So circuit board communication. So let's kind of break that down. So when we're dealing with cellular, the IoT cellular devices, now this may be different on higher end devices, but on these devices, you have two typical communications. You have USB, you have UART. They almost always have two UARTs. I want to mention that. One of them is a debug UART. So you can plug into the debug UART. It's mostly available. And you can watch the chip boot up. It has some kind of embedded operating system. And you can actually see it boot up. The device I have on the board over there, EG91, comes up with an actual logon prompt. So if you can get a password, you can actually literally log on to the cellular module. When you get into USB, interchip comms, there's three standard types of USB communications. There's what's known as high-speed interchip. You have eUSB. I've encountered eUSB on devices that may communicate USB from one board to another board, because obviously sometimes when you get into more lower power USB communications, length is an issue. eUSB gives you the ability to do that. You can go from standard board USB to an actual real USB over a regular cable back into inter-circuit USB or high-speed USB. It's usually called eUSB. I've seen this actually used on communications and solid-state drives on certain embedded type devices, where the solid-state drive was on another board or another system. And that was the first time I came across eUSB. And then you have standard, which is low speed, fast speed, and high speed. The super speeds, I've yet to see these on an IoT device. There's rarely a reason for it. Also, the one thing to think about, USB and interchip could easily be a substandard. So high-speed interchip will be a substandard of 2.0. So when USB comes up, it basically queries out, says how many devices are out there, because you can have multiple devices on USB 2.0. We're looking at an embedded device. You will not have multiple devices on USB. So sometimes that functionality will not even be executed, because it already knows the identifier is 1, because there's only one device on the bus. Any questions? Is this all making sense? You know, I do live in a dark room, so sometimes I don't always communicate with humans all the time. So let's get into USB communications. So the device I'm using is a Beagle. This is not cheap. It's about a $1,300 device. I am looking for somebody producing an open source. The problem is if you go out and look at USB sniffers, they're all inline USB sniffers. That means data in, data out the back side of it. If you're doing interchip communications, which travels 3 centimeters, you can't stick a device in between. Plus, it's usually a lower power level, so you'll instantly drain the circuit down and it will quit working altogether. This particular vendor, and I hunted for a while, this vendor claimed in one of their data sheets or from a question from somebody else that you could do this. So I'm like, okay, I'm willing to gamble $1,300 on that. It's my company's money anyways. So I bought one of these only like about 2 months ago, and I finally got to look at it like 3 weeks ago. So about 3 weeks ago, I was looking at this final phase of this. In this particular case, you see these devices. Sorry, I'm going to get in here. So you see this hooked up right here. It turns out for the USB sniffer to work, it has to detect basically has to detect V-bus. So normally on USB cables, you have ground, you have V-bus 5 volts, and then you have D minus D plus, which is the data lines. When you look on the chips, V-bus is never brought to the surface. It's underneath the chip, so you can't even tap into it most of the time. Not easily. I may mention another method here in a little bit to potentially get access to it. So you just lie to the Beagle. So I set up a 5-volt power supply. In this case, I just used a 5-volt power supply, a little one you plug in, and I just hook 5 volts to it. So it says, yeah, there's a device there, of course. And it works pretty good. So, but to connect to it, you can't connect right to the USB lines. You'll instantly overwhelm it. So the vendor says you need to put a 20 to 40 ohm resistor in there. So the best way to do that was, let's just wire it onto the board. So I went ahead and I soldered in. So this is the bus here. And it had 2 resistors in line. It was interesting. So I'm looking at that and I'm like, hey, there's 2 resistors in line. I've seen that before. Those resistors measure at 0 ohms. So I'm not sure what their purpose is in this particular case. Maybe it was to just disconnect the circuit altogether at one time, and that was just being used as jumpers. So I added 2 33 ohm resistors in there, and I wired the device up to it, hooked the device up to it, hooked it into my device. Now let's go ahead and do a demo so we can see this thing working. So this is a live demo. No chickens lost their life in this process, so I'm not sure if it's going to work, but we'll see. Looks like I'm going to have to end the show. Okay. Okay, what do we got here? This will be small, but I'll blow it up as we start getting real data. So we're actually connected to it right now, and you'll see some stuff take place. So this is the rig I have right here, and it happens to be one of these. It's a cellular field camera that we got hooked up. And let's see if I turn it on, whether it'll come on. Oh, yes, it did come on. So we're starting to see things happen here. Got to wait up. The USB is actually doing its game as it powers up, and the CPU powers up, and it starts communicating with the device, and boom, we're actually communicating with the device. So if we come over here and I select filter only on data, now we get to communication data. So we can see there's a lot going on here. We can see it pass this data right here. So we can see it sending bill mode information, upgrade information, is checking all this stuff out to the actual device. Now this device will actually connect out to Amazon S3 Cloud. This may take a minute. It's set up to detect motion, but it's kind of odd and slow at it. Hey, you know, it is a field camera. It isn't the smartest thing in the world. But we can see the data continue flowing, billing, and you see a lot of commands here. Data being passed, different commands, cumulative status. Let me find one that's more interesting. Here we go. This is actually the modem validating connections to the actual services out there. So we got that. And interesting. Some of it's boring, but there's a lot of data in here, and you get to see the entire functionality of this device communicating between the primary CPU. Let me see if we can find something else that makes sense. Okay, here we go. We can see this. This is actually, and you'll know, this is the actual service, mcmiot.us, like you would call Verizon. This is calling out to this service here. So there's a bunch of data in here, and we're going to get into some interesting things in a minute. Let's see if this thing, I'm hoping it'll actually take an image, but it never does it when I want it to. So we're going to move on with the presentation, and then we're going to come. Yes?
So I have several questions actually. Number one, what tool is that you're using?
This tool is the one put out by the, what's the name of the company? Total Phase. It's for their products. Multiple products will actually work in this, but
does it capture like handshakes right now, and can you save that data?
Yes. So you can save all this data out in comma delimited format for parsing later. You can also, I read a reference where one of the guys he didn't share it, but he wrote a script to convert this data into PCAP structure and then import it into Wireshark. So it would be possible to do that and potentially pull the graphic images or the videos or things out of the actual communications. So you have that data. So we're going to talk about some attack vectors that I have not done that are potentially there as we kind of move on. But let me see if I can get the slide deck back up, if I can figure out where it's at. And we can slideshow, play from current slide. And we're going to let this run and kind of move on and come back to this. I'll be back over in a second doing something else. So the next thing I want to talk to you about is how do you control, as you saw in that picture, how do you control a cellular modem? You control it with modem commands, AT commands. They're very customized, so they're not the old Hayes modem ones, at least not all of them. There may be some like that in there. And it varies based on the product and the vendor and stuff like that. You could do file services. You could do firewall and socket services on these, FTP services, MQT, HTTP. We're actually going to take this field camera and we're actually going to download a web page with it here in a few minutes by passing commands. Yes, sir?
So
there a relationship between the AT commands and the like 3-digit numeric commands that go with that, with a star or pound sign, that maybe can get various data out of your cell phone's controller?
I'm not familiar with that. No, sorry, I haven't seen that. There's a whole list of commands. So I will be releasing. So I'm working on a paper right now where we document some of these processes and thought patterns and stuff like that, hopefully before DEF CON. At the same time, I'm going to be releasing some Python scripts that you can use on these devices. So one of the things we found out, and like on this device, what we did was we took all the AT manuals that were available online. I need to double check we got them all. We downloaded those and parsed all the AT commands out of those and put it in an automated Python script. So you can actually, if you want to know what the command structures are, you can read the manuals or go online and search. But if you want to know what's available, you can actually make requests with basically this Python scripts to the device, and it'll test every one of the commands and give you the command structure back. So you can ask what the structure of the command should be. It'll give you that data. And you can also run it to actually pull the data that's actually stored on the cellular modem off. And we've kind of automated all that to give you everything. And then we also created some weird fuzzing scripts. So basically you can go, you can type in the name of the command, and it'll actually query the device, tell you what the command structure is. You can say, oh, that's 4 variables. You say, I want to fuzz 4 variables, or I want to fuzz, and it'll go, which ones you want to fuzz, and you can go, I just want to fuzz 1 and 3, and then it'll let you fill in everything with the data you want, and then you can feed a fuzz file into it to just start dumping data into a particular command structure. We haven't found anything interesting doing that, but we haven't really sent it any really workable fuzz data. It was just proof of concept. Let's see if we can even do this. Usually I just overwhelm the modem and crash it. So you have to put timing in there and figure out what the timing is to make it work better. We're going to talk about some other stuff. So let's, UART injection. So to be able to do this, what we did was, as I mentioned before, yes?
Sorry, about the fuzzing, what kind of fuzzing do you do? Do you just use more already existing messages?
Yeah, it would be the command structure. This fuzzing here we're talking about is using the command structure that's available, AT command structure that's available in the modem. Yeah, we can set it up to automate it. So we've automated all that and say, hey, this particular variable or value for this command, we want you to feed all this data into it one after another and record the response back. So we record all the response back and put it out into a file. Again, the data we were sending into it was not interesting fuzz data. It was just a test file with junk in it, just to make sure we can get the process working. So the UART injection commands. So in this particular case, we traced out the runs from the module. We went ahead and we cut the runs, cut the actual runs here, routed it out to a breakout board where we actually have the circuit turned off. The cool thing with this device, now when you encounter these devices, there's 2 ways for it to take data or commands. You'll never have them doing both. It's either USB or it's UART. The weird thing with this is the first device I've seen that had USB, but the UART was still connected even though it wasn't using it. So since the CPU really wasn't communicating anything, we just break the circuit. But the modem would still respond back over the UART and tell us when it's ready or any commands we send to it and all that stuff. By cutting the runs, it gives us the ability to get in there. If for chance it isn't connected, which is common. If it's all USB, the UART may not be connected. So getting commands in it is more problematic. So how would you do that? If underneath the chip body, those connections were not connected. Well, it turns out, like I mentioned, all of those exist around the outer edge. And we found out through testing, and it'll be in the paper where I show this, on smaller devices, like we looked at like a BG95 as an example, those LAN runs were closer to the edge, and we were able to insert acupuncture needles underneath the chip body to gain access to those circuits that weren't available to us. And it worked. Now we tried it on the larger EG91s. more problematic because it was 3 millimeters in, about 3 millimeters in before the LAN grid started. And the chip, the way it was, slightly bowed, so it was closed and we couldn't get to it. Now I did attempt to method of actually side drilling right where the two meet, but I couldn't get any kind of real precision with that. And all I did was just maim a bunch of boards and chips and wasn't successful. I wasn't about to try plugging stuff up to this because I did see way too much damage to it using pin vices with drill bits that were really small. And no matter what, they still tore things up too much. I needed a more finer hole to be able to make this successful. Because we also tested taking the needles and actually coating them with solder mask and UV in them so that they wouldn't short out, as an example, too. Total fail. Yes, sir?
I wonder if a high-powered laser might work to whip the blade away.
Probably.
CO2 laser right in the right spot to blast some of that away.
Yeah, so the big thing is you got a multi-layer board, so you got to be careful about hitting one of the layers in there. And then you have typically the ground plane sitting there also on the main board, and you got to worry about that. Now, for the ones where we were just able to enter the needle, we used Captain Tape, covered the board with Captain Tape, and then slid the needle across that, and we were able to put it in without shorting out the components. So let's go ahead and look at this. Oh, we're running out of time. This getting close to finishing up, but I want to talk about some of the stuff. Okay. Let's end this show again. So we should be hooked up. Okay, so I'm hooked to the UART, so you've seen the thing go ready, power down. That power down is the power management system kicking in, powering it down on its own. But I can bring this back up. Oh, it's back up already. There it goes. Start back up. And I just wanted to run a couple commands to show that we're able to do that. Don't do that to me. Okay, so it's ready. So now we can just enter AT commands on this device. It comes back okay. We can actually send data there. We can get information about the band that's connected to on the device. Let me see if I get this smaller. There we go. Let's come over these commands. Get these. What's that?
Are these commands going into the UART?
Yes, they are. These commands are going into the UART. We're able to attach to the UART. Let me shrink this thing down because I'm not typing these commands.
What speeds are typical for the UART?
I've seen 9600 actually used. Remember, a lot of these devices that just use the UART aren't moving massive amounts of data. It's just telemetry data, so they'll do it low. But almost always 115200. And let's look at another one. So another command. Let's see if it hasn't shut down yet. It hasn't shut down. That one gave me an error because I copied a T in there. So AT plus CGDCON. And this basically, I don't know why it's turning back an error on that one. That's kind of odd. Let's go ahead and try it. It's a possibility something ain't working on it, but we'll check. So with that, we can send all the AT commands available. This device had a bunch of commands that weren't in the actual manual. So what we're going to do is, let's see if this will work. If we can get it before it shuts down on us. So we're going to actually connect it out. We're actually going to point it to a website. Okay, and then now we can do this before it goes to power down. There we go, HTTP GET. There you go. So we're actually able to take this device. So we can do FTP connections with this. Let's real quick. Let's jump back over to the actual this device here and ASCII data, and I want to look at bucket. I'm hoping it actually moved some data. Yes, it did. So now we moved some data. So now if we come down here, look at this Is that one it? Is that it? Ah, here we go. Let's look at this one. I'm not going to look at all the data because that would like give you all my freaking keys. So you can see we're actually connecting out. We have a client ID, so now we know my client ID, secret access keys that we have there. Well, let's kind of go up to the other one. Let's see if this one will give it to me. No, that won't. One of these. Well, I don't want to give you all my keys. But as you can see, we actually connected out. I thought this would show me the, hold up a second. No, let's come over here. But it should show, there, you can get more of my keys. You got it all yet? So we can get all the keys, but it actually connects out to the S3 bucket. And it's all the data. So that gives us a lot of information from a security standpoint if we want to be able to test actual devices. And we're going to talk about that before I get shut down here in 10 minutes. Play from current slide. So we have some things, so we know we can get this device to connect out and do some stuff there. But the truth is, and I haven't done this yet because I haven't had time, one of the things, in this particular case, I could get to anywhere on the internet, okay? Often what we run into with some of these devices or some of these services, they actually have private VLAN connections on the cell, okay? That means the back-end data, cloud data, or private clouds are not accessible from the internet, only from these devices. I've seen devices doing that. It's not uncommon. This is cheap Chinese stuff, so they don't care. So what can we do? So from an attacker perspective or a security tester perspective, because that's the direction I come from, if I'm testing a product's overall ecosystem, how do I get to those back-end systems? By doing what we did. Now we're on that modem, I can send commands to it and potentially gain access into that private VLAN through the device its actual self. And one of the things I haven't tested yet completely is this particular device also has this QI open where I can set up sockets. So when I get back home, I already started the Python program for this. We're actually going to turn this into a port scanner where we tack into the UART and we can port scan the back-end virtual environment. It'll be slow as hell, trust me. But the goal is if I'm being paid to assess your security of your overall products ecosystem, I want to look at the whole ecosystem. And I want to make sure certain things. So what would I be thinking about to look for? One, those keys that were being set up to gain that access, are they unique? Or is the same key and authentication into that service identical across multiple products? And then the only identifier is, the individual device number. Or if the device can connect out even with different keys, how much of that virtual environment shared? Because is it a real private VLAN per device? Some manufacturers do that. I know a couple of them that actually do that and do it right. But if they aren't doing it right and it's a shared back-end environment, instantly it's a risk. Because now I could purchase your device, use that as a tunnel. And then this is nothing but a cell modem. Okay, on the device. There's nothing saying I can't pull the SIM card off that, pull all the data we just seen go out, plug all that information basically into a development board, set up USB net. This device actually uses USB net to set up a connection for the underlying operating system to be able to pass data. It's just none of it's encrypted, so we're able to see it all. But it's network actual data. So you could easily do that, basically turn a development board into a network interface card using all this data, and then I have full access via the network. That is for devices that pass large amounts of data and follow the USB net setup function. If they don't do that and just move telemetry data, the attack vector becomes more complex. The smaller devices may not have all these functions. But if there's any functions that you can control to set up on that modem, you can turn that into a port scanner. The FTP can be turned into a port scanner. Because all we want to do is go, hey, am I getting a live connection? Doesn't matter if it gives me any useful data. If it times out and gives me no connection, we know there's nothing there. So it's all based on back error messages and timeouts. I can literally port scan an entire environment doing this, no matter what features are available, if there are any communication features that I can control. So here's some references. The paper on interchip communications I released a couple years ago. I spoke here last year on that. Check out the paper. I think it's a great write-up on how that all works. And we released a proof of concept called a Karen proxy, which basically gives us the ability to cut UART connections, route them out to a breakout board, and set a proxy on top of it. We can control all the flow, capture data, replay it, and inject our own data automatically. Or actually replay data and have it say, you see this bit sequence, replace it with this bit sequence. And again, it's still a proof of concept. So any questions? Because we're kind of like at the end. Yes?
Have you looked at any medical devices using cellular modems similar to this?
No, I have not. You know anyone who'll give me some?
In 5 years, I would give you one.
Okay. Yes, sir.
So maybe I didn't catch it, so apologies in advance if you said it, and I'm asking again. I saw your board and how you have very tiny wires and how you did the soldering with precision under a microscope. How finely tipped did the soldering iron have to be able to work at such a small scale?
Mine's 0.2 millimeters.
0.2 millimeters?
0.2 millimeters. My rig's like a $1,200 rig, so it has a micro iron for doing that stuff. The saving grace, I've done it with a Hackos. It'll work. The balls that I put on there is the winning part. So what I do is I take the wires, I put solder on it, and I run the wire in. Those wires are covered with lacquer. I burn the lacquer off and tin them. Then I clip it under a microscope, so I'm left with just like a 0.1 millimeter on there, and I stick it against the ball and then just tap it with an iron. And it instantly sets up, and then I hold it in place with E6000 flexible glue.
You plug the solder into the wire, and then you kind of heat up the solder.
You don't have to do that. I do that just to avoid some issues because I want to make it quick. So when you're working, you've seen the chip. When you're working with something that small and you hold an iron on there for more than a couple milliseconds, who knows what damage. And if you want to get good at it, I always tell people, do what I do. Drink like 3 or 4 big things of coffee before you start. And when you learn to control your hands in that condition, you got it mastered. Well, I'm almost out of time. Also, I want to point out, what we demoed today is not a diss against this product manufacturer. Now, I haven't put the product out there and told you what the product is. But they have really, I have not looked at them from a security standpoint nor tested their product from a security standpoint. This is purely a functional demonstration of how technology works and how you can leverage the normal functionality of technology for a potential method for attacks or security testing. So don't go out there and say, oh, these manufacturers are doing it wrong. You know, most of them are not. They're doing it based on how the technology works. And us as hackers, what's our job? To take that technology and use it to our advantage. So thank you very much. I appreciate it.